Right, well, this is going to be the last paper of this session, and then afterwards we'll circle back and have maybe a little bit of a broader discussion. So the questions that didn't get answered, we'll try to circle back to. But our last paper is Judy Rochat and Herb Singleton.
Good morning and good afternoon. This is Judy Rochat from Cross Spectrum Acoustics, and my co-presenter is Herb Singleton, also from Cross Spectrum Acoustics. We're presenting as part of the tutorial on sound level meters on the topic of practical tips on use. We're covering 5 subtopics today. The first is calibration best practices, then when to use a windscreen, deploying a sound level meter, choosing settings, and background noise. We'll get started with the first topic, calibration best practices. To help discuss calibration, we define the term 3 ways in this presentation. The first is a laboratory calibration, abbreviated lab here. This is where you send a sound level meter to a certified lab to have it calibrated. The second is to establish sound level meter sensitivity, abbreviated here SETCAL. This is an in situ amplitude sensitivity adjustment using a reference level sound pressure signal, for example, a calibrator. And the third is the measurement of the reference signal, or check cal. This is also an in situ measurement using a reference sound pressure signal. For the set cal and check cal, all of the components of the measurement system should be included. This includes things such as the microphone, preamp, sound level meter, interconnecting cables, signal conditioning components, and audio recorders. So starting with laboratory calibration, to maintain a sound level meter performance, a calibration laboratory can measure, check, confirm, and provide documentation for performance testing, and should provide a dated and signed calibration certificate. In some cases, especially when a calibration laboratory is operated by the instrument manufacturer or distributor, the lab may be able to adjust internal settings that affect acoustical performance. So how often do you do this? Some agencies or standards require annual calibration. The current thinking is that the sound level meter manufacturers should recommend intervals, and these may be based on the history of calibration adjustments made with a particular instrument. However, for now, we need to adhere to agency and standard requirements unless you've arranged otherwise. So now you're in the field or the lab to do measurements, and the general process is to assemble your measurement system, do a set cal to establish the sensitivity, do a check cal, note the level, collect data, check cal again, note the level, and save the data. A couple cautions on the set cal. If you need to reestablish the sensitivity after data collection, it should not be done until after you've done a check cal and documented the level. Also, some sound level meters will discard all the data when you do a set cal, so make sure you know what your instrument is doing. For a calibrator, when you're using it, don't just slam it onto the microphone, or else you may disturb the diaphragm. Place it gently and make sure it's properly seated. Also, when placing it on and removing it, turn it slightly clockwise to prevent the microphone from unscrewing. You can also check the microphone gently with your fingers to make sure it's screwed on properly after you've removed the calibrator. Another thing is to ensure that the calibrator is turned on before doing a set cal or check cal, or else you could confuse yourself or your instrumentation. For the level, calibrators have multiple outputs, for example, 94 or 114 dB, and you should select that level with optimization of the dynamic range of your whole system in mind. And that level may be 94.0 or maybe 93.9. You should check manufacturer's documentation because that level could depend on the microphone size and type. Also, some sound level meters require input into your sound level meter of the reference level. And if you set this improperly, you'll notice it during data collection, but you can correct for that during processing.
Good morning and good afternoon. This is Herb from CSA. Windscreens are used to reduce or eliminate wind-generated noise or pseudo-noise on the microphone. Windscreens can help reduce noise, but only up to a point, so it's advisable that noise measurement should only be made with a wind speed below 5 meters per second or about 11 miles per hour. Wind-generated noise on the microphone may also be difficult to avoid with most windscreens when measuring sound levels below 40 decibels. While the primary purpose of the windscreen is to shield the microphone from wind noise, another secondary benefit of a windscreen is to protect the microphone capsule if the mic is dropped or if the SLM stand is accidentally knocked over. If you're unlucky enough to have dropped a microphone, at the very least you want to inspect the microphone for visible damage before using it. However, the best course of action is to pull the mic from service until it can be properly evaluated. Windscreens come in a variety of forms as shown in the pictures on this slide. Windscreens should be clean, dry, and in good overall condition before use. Take care when storing windscreens to avoid deforming foam-type windscreens and to prevent exposure to the elements. Acoustical measurements typically use a 3 to 5 inch diameter windscreen. If measurements need to be conducted in high wind environments or in quieter environments, larger windscreens with diameters of 7 inches or larger can be used. Using a windscreen will somewhat reduce noise levels at the microphone, especially at high frequencies over 10 kHz. For the most part, these insertion losses will be under a decibel for A-weighted measurement and can usually be neglected. The exception is when using larger windscreens or denser waterproof windscreens, where reductions might happen at frequencies as low as a few kilohertz. Deploying a sound level meter. The type of microphone that we use and how it's oriented relative to our noise source can have an effect on the accuracy of our measurement. The frequency response of the microphone will change depending on how it's aimed towards a given noise source. The frequency response difference typically occurs at about 1 kHz and above for 1/2 inch microphones. The manufacturer can provide curves of the frequency response as a function of microphone orientation. The illustration on the slide shows the microphone capsule and examples of sound waves arriving at 0 degrees or normal incidence along the axis of the microphone, and at 90 degrees or grazing incidence across the microphone diaphragm. The high frequency sensitivity of the mic at grazing incidence is lower compared to the normal incidence orientation. However, the microphone may be optimized for flat frequency response at normal incidence, grazing incidence, or somewhere in between, depending on the microphone type. Because the frequency response differences occur above 1 kHz for a 1/2 inch microphone, corrections to account for orientation are usually not required for A-weighted measurements. Care should be taken if the measurement is trying to characterize high frequency noise. This slide shows examples of microphone orientations for various measurements. The top photo shows an example of a microphone positioned vertically and optimized for grazing incidence for a highway noise measurement. Although the noise source is moving relative to the measurement position, the angle of the sound wave at the microphone will remain constant and reduce measurement error. The middle picture shows a normal incidence measurement where the microphone is pointed directly at a sound source. This orientation is best for stationary point sources, such as generators or idling vehicles. The bottom picture shows a random incidence microphone pointed at an angle of about 70 to 80 degrees from the ground. Pointing a random incidence microphone directly at a stationary source will tend to slightly overestimate the noise level, so the meter is angled to produce a more accurate result. Sound level meters are generally available in handheld form factors. However, it's usually preferable to have the microphone or sound meter supported on a stand positioned away from the operator. While handheld operation may be convenient, the body of the operator can sometimes interfere with the sound field and affect the measured data. If the meter is going to be held in the hand, the operator should hold the instrument at an arm's length as far from the body as possible and to one side to minimize such effects. However, using the meter in this fashion can still influence the sound level up to about 1 decibel at various frequencies. Having the microphone or SLM on a tripod usually means that the effects of the tripod or stand are minimal and can be ignored. A tripod also provides a more stable support than handheld operation, especially for extended measurements. Setting up the sound meter is extremely important in terms of making sure we acquire meaningful data that conform to project requirements. Noise measurement standards, policies, and guidelines will list metrics that will help to select appropriate settings. Using this guidance, consult the sound meter documentation to determine appropriate settings. Keep in mind that the language used by a particular meter may differ slightly from that used by the relevant standard or policy. For example, SEL versus LAE for sound exposure level. If your meter can store settings information, use this function to store or list commonly used settings. Also test your sound level meter to make sure that the measurement, download, and processing functions are working correctly. This slide lists some of the major settings that should be considered for a given measurement. There's not time to go through all of these in detail, but I'll go over some quick points. Consult the written paper for a more detailed discussion about these settings. The acoustic metric, such as LAQ, LMAX, and so on, will usually be determined by project requirements, standards, or guidelines. For frequency weighting, most modern sound level meters will offer options for A weighting, C weighting, and Z weighting, or no weighting. Exponential time weighting sets the slow or fast weighting response of the meter, which will be selected depending on if the source of interest varies quickly or slowly over the measurement period. Time interval can refer to a number of different concepts, and it is important to understand the nomenclature used by a particular meter and to know how data are collected and what is reported. Finally, dynamic range represents the range of sound levels that can be measured by the meter, and it is important to understand the capabilities of your meter and, if necessary, to set an appropriate range to account for expected sound levels during your measurement.
And now we're on our last subtopic, which is background noise. When conducting noise measurements, it is important to consider background noise, which is defined as the all-encompassing sound of a given environment, excluding contributions from the sound source or sources of interest, unless, of course, the source of interest is the background noise itself. There are two primary cases for measuring background noise. The first is to know how much the background noise may be contributing to noise levels measured for a targeted noise source, for example, a train or computer fan, and the second is to establish existing noise for the purpose of determining acceptable threshold limits for noise increases due to a proposed new noise source. In these cases, it is important to conduct measurements at times that are representative of the environment and remove any noise sources from the data that may have been intrusive or not representative. A noise engineer will often need to make a judgment during measurements as to whether or not an extraneous noise source is intrusive. And this is one that is potentially contaminating or influencing your noise source of interest. So when you're collecting data, the start and stop times of intrusive noises should be noted for later examination and potential removal of the intrusive noise event or a time block containing the event. So what if you do have background noise and you're interested in extracting the targeted noise source? For broadband noise, if the targeted noise source minus the background noise source is greater than or equal to 10 dB, then the background has minimal contribution and the level is representative of the targeted source. If the targeted source minus the background source is less than or equal to 5 dB, and this is for broadband noise, you cannot determine the source level. If the targeted minus background noise is between 5 and 10 dB, you can adjust the level to determine what the targeted source level is using the following equation. And you can find this and examples of using the equation in the U.S. Federal Highway Administration's Noise Measurement Handbook. Now, if you're interested in particular frequencies and not just background noise, it may be possible to extract the source if it's well above the same frequencies in the background noise, even if the broadband sound level is within 5 dB. To wrap this up, we'd like to refer you to our paper for more details and tips on calibration best practices, windscreens, deploying a sound level meter, choosing settings, and background noise. Also, we'd like to thank Dave Reed of USDOT Volpe Center for his valuable input. And as a reminder, there are other papers and presentations available for the sound level meter tutorial series.
Great, thanks a lot, Judy and Herb. We have a couple questions, and then maybe we'll open it up to a little bit of a broader discussion. So Herb has a question from Owen King. Have you ever heard of measuring at ground level to minimize wind effects? And he says, particularly for wind farm compliance measurements.
So the answer is yes. So for wind farm measurements in particular, there is a standard, I forget offhand if it's ISO or IEC, where for wind turbine sound power measurements, the standard calls for measuring the microphone at ground level. And I remember Gunnar Rasmussen mentioning that he's done a number of experiments and found that measuring at ground level for environmental measurements tends to produce less variability in the results. The downside is whether or not the measurement at ground level is representative of whatever you're trying to characterize.
All right, we got some more questions. I'm kind of jumping around on these. I apologize. Some of these are going to be a little specific and a little more broad. So Adwait Ambaskar asks, could you comment more on the variation in frequency response of the sound level meters for mounting on a tripod versus physically holding the meters while making noise measurements? And maybe along with that is, how is the frequency response affected by the proximity of the measuring person to the meter? So how much does it matter if it's on a tripod or if you're holding it away from you or if you're holding it, you know, right next to your body?
Well, we do know that based on what we researched, that you can get about a dB influence if you're hand holding the sound level meter versus mounting it on a tripod.
Oh.
I don't know that I have any more answers for the other part.
I mean, so presumably the kind of usual, like, how big are you compared to wavelength things,
right,
would apply. Hold it away from you. So
I mean, we've done that testing as well. This is Jim Weir. We've done that testing, you know, with and without tripods, and we train people, don't use a video tripod with a big knuckle right underneath the meter. Get the meter away, because, you know, we're talking about 3,000 hertz with it gets a very significant wavelength relative to the size of your meter, let alone adding an inch grip with my ham hands grabbing a hold of a meter, right? You want to optimize the response at best in your precision. But yeah, typically over a dB, just tad over a dB for that. We've done tests when you chest a meter, you know, like when I do a training for a police department, a lot of guys will just hold the meter in their chest, and just with a broadband noise source, we can get a dB change in the level versus holding it away just by the reflections coming off the body. So you do want to get it away from your body.
Okay. I think we'll do one more question in this, and then, but we're all going to stick around for additional questions because there's not actually a paper after this one. So we'll go to Sunit. If you're measuring sound pressure level on top of a building kind of long term for a couple weeks, and how do you account for the windscreen to potentially induce an error in the measurement for days when the wind was too much? Do you just live with it? Do you delete that data set when the wind is too high? Is there some point where even the windscreen is not going to do what you want for a high wind condition?
Yes. So it's recommended not to measure when the wind speed's about 11 miles per hour or higher, because there could be contamination on the microphone. And actually, if there's a recording along with that, you should be able to hear that contamination, and that data should be removed.
Sounds good. So this is technically the end of this this session, and but we're going to stick around. if people want to jump off and go, you should be able to catch the last paper in one of the other sessions, or the authors have all agreed to stick around and have kind of more open discussion. I do want to remind everyone there is the continuation of this session in an hour from now. So that's at 3 o'clock New Orleans time, and we'll see a couple more tutorial papers that are going to be great. But let's go ahead and switch to a more open discussion, which is sort of the same. One thing that has come up that I don't particularly care who answers. I'm not going to answer it though. Rick Colano wants to know the difference between random incidence microphone and diffuse field or pressure microphones. And
I mean, I guess Jim. I can jump on that one just because it's it actually goes back. There's a little history to this, right? So with the ANSI standards, they used to always require you to use a random response microphone on your sound level meters for a type 1 microphone. And that was up until about 2014 or so, where the ANSI standard became aligned with the international standard for sound measurement. To make if you're designing a microphone for flat random response, the tuning of the microphone in its resonance for upper frequency limits has to be a little different than what we would normally call a free field microphone, one that you point at the sound source in sort of in a open environment like outdoor noise or something along those lines. The free field microphone has a rolling off pressure response in the high frequencies above 5 kilohertz because the sound pressure itself, as the wavelengths get smaller, build up in front of the diaphragm. So if we want to measure sound accurately, pointing the microphone at a noise source, we have to correct for that. And that's what is known as a free field microphone. A diffuse field microphone sort of takes the average of all the directions and has no one direction where it's perfectly accurate, but on the average across all directions, like a community noise measurement or measuring in a building for workplace noise exposure, those kinds of things, you would want a diffuse field microphone because at best it's on the average direction of sound. And that's also the instrumentation that ANSI specified. And so the guys at ANSI said, well, what if we want to measure a free field a source like a highway, and I want to pick up the sound levels accurately as possible with a random diffuse field microphone. And they determined that you should tip the microphone up, 70 degrees or so, off of pointing straight at it. In other words, up at a little bit of an angle. And that's why a lot of times when you see pictures of sound level meters on tripods, they're stuck at an angle up. And that's because they're using a diffuse field microphone to measure a free field response. And I guess the related question to that is, what if I screwed up and did it wrong, right? What if you tipped it up on an angle when you didn't really need to have it on an angle, right? If you had a free field microphone, you should have been pointing towards it. Well, you'll be a little off axis, but if none of the noise is above 5 kilohertz, it really doesn't make a big difference in your sound with a 1/2 inch diameter microphone. Anybody else want to add to that one?
I think that covers it pretty well, Jim. There's some, I mean, the difference is, Andrew, maybe you can comment on, like, the difference is just kind of where the port is, right?
Well, it's also the design of the backplate. So you can tune the response of a microphone by designing the backplate behind the diaphragm. So, and that's a proprietary feature to all the manufacturers have their special sauce in their own backplate design. But that's really how they do it mechanically to do that.
Awesome. We're going to go to a question for Judy. Brian says it's good advice to verify the calibration tone before and after your measurement. How much variation is too much? If it's 4 dB apart, do I need to throw out my whole day of measuring?
4 dB, probably. What's considered to be acceptable is usually if it's less than 0.4 dB. You don't need to make any sort of correction for data. If it's 0.4 to 0.5 dB, there is a correction that you can make. And if it's greater than 0.5 dB, you probably have an issue, and you would need to scrutinize that a little more. There's guidance on how to do that as in the Federal Highway Administration Noise Measurement Handbook, if you want to see the equation to use to make the corrections when it's 0.4 and 0.5 dB.
Yeah, also, if I can chime in, one of the ENZ 12 I forget, one of the ENZ community noise standards, the one that has like 6 parts, they have some guidance also on calibration drift and what's acceptable and what's not.
Awesome. So we've got time for some more open discussion, but while we still have a lot of kind of attendees here, one thing that I wanted to bring up is this is, like I said, this is kind of a group effort to do this tutorial session. Based on the number of people that are attending here, not everyone can see that, but we can see the numbers. There's over 50 people tuning into this tutorial session. We might try to do this more in the future, but we're not going to do sound level meters again. So if anyone has suggestions on other things you'd like to see kind of a multi-talk tutorial on, you can put that in the Q&A as well, and we'll rope somebody into doing a talk on it in the future.
Yeah, and feel free to reach out to Tyler or I, as the organizers at any point, whether it's in the Q&A now or in the future, about topic ideas for next year, or whether you found these talks helpful or not, whether they're too simple, too complex. We're still working on hitting the sweet spot.
I think it works from my perspective. It works to have a little continuity between the different talks, and it really frees up some time to go more in depth than we could have.
We didn't answer Brian McMillan's question about ELSA-BEN standards.
Oh yeah,
that was from the first session.
Yeah.
He's right. There really aren't a lot of defined standards. You can go to the ASTM or the ANSI community noise standards, and they reflect the definitions of ELSA-BEN and how they might be used for a limit. The closest I can find is they want you to kind of capture the data in 1/10 of a second intervals to get a reasonable amount of statistics. Yet I know other community noise standards, for instance, the FAA around airport noise, allow you to do stuff based upon 1 second LEQs. In Europe, also, there's some recognition that 1 second LEQs is probably the longest session you can get to evaluate sound for long-term effects. If you did it for, say, 5 seconds or 10-second intervals, that doesn't make sense. When they do specify a parameter, often it is, I think I said in my presentation, it's the fast weighting that is used to create that, again, because that's based upon the dynamics of sort of the human ear and how it works for perceiving loudness. And whether you capture it once per the fast every 1/10 of a second, it makes kind of sense to do that, or at least every 1/10 of a second. I think we capture 100 times a second minimum when we look at our levels in our instrumentation, but it makes sense to capture at least more than once a second to optimally respond to the extremes. We can do a test real quickly and compare the two, and I've done this for a customer where you capture the 1 second data from LEQ log data, and then you also capture the raw statistics from the meters measured every, however fast the meter does it. It varied from one meter to another in our portfolio. That you only see the real difference in, say, you don't see it at L90, you see it at L99, right? You don't see it in the middle. You see it at the frequency extremes if you change from 1 second sampling to 1 second sampling to the fast sampling at a faster rate.
If I can follow up on Jim's statement, he's correct in that it's haven't found a standard for doing that, but also the actual algorithm for doing the statistical percentile calculation, there are different ways of doing it, and they can give you slightly different answers. If, having found this, trying to re-implement statistical calculations in MATLAB or Excel. So, so I guess they're probably not huge differences, especially over long averaging periods, but it's just something to be aware of.
All right. Maybe I'll read this one. I'll read Ted's question for you, Andrew. So Ted Piper is asking, ASTM E336 allows for manually scanned microphones to measure background noise. You want to get a spatial average of the sound field, but you can't do that if it's on a tripod. So what do you do instead, Andrew?
Yeah, so I'm just going to recommend everyone come to the next session, because Owen King and I are doing a paper on sound level meters and how they're used in the standards, and we actually talk about how you do scanning of rooms, both handheld and mechanically. So come check out our session, and we will hopefully answer your question in great detail. And if it's not enough detail, feel free to ask another question then.
And if you want even more detail, the best way to learn more about noise control for those that are new, there's a series of courses on noise control engineering offered by INSUSA. So if you go to insusa.org and look at the education tab, there's a series of 3 courses, and 2 of us are here that teach those courses, and it helps to meets most of the requirements to become a board certified noise control engineer. So for those just starting out in the field, it's a really great way of getting a lot of education quickly.
And just back to Ted's question real quick. If you're mechanically moving a microphone or a sound level meter, there are basically turntable systems out there that allow you to do that. And you just need to be careful about how you set those up. So you don't set them up in a single horizontal or vertical plane in a room. You would set them up in sort of a cross plane. I can get my hand in the right position on the screen or something like that. And the microphone would then rotate like this, right? So there are systems out there you can buy to mechanically move microphones around to spatially average.
Awesome. Mark Levko asks, what's the deal with the impulse setting on meters? They used to have fast, slow, and impulse, and maybe they don't so much have impulse anymore. Jim, can you answer that?
Yeah, I can give that one a whirl. So the impulse standard dates back to the early 80s, and there was what's it called? EC. There's a equipment noise standard for things like line printers and things like that was really important back in the days when office machinery made lots of noise. And that standard took into account the difference of the ways humans perceive the annoyance of sound differently based upon whether you know the or impulsive sound, I should say, based upon whether or not you know the sound's going to be there or whether you don't know the sound's going to be coming. And so if you don't know what the sound is going to be doing next, then the fast waiting correlates pretty well to human perception. But if you do know the annoying sound is going to happen, imagine an old-fashioned line printer, or if you're going to a place where you have lots of sound, you're expecting that, a bowling alley, whatever, your brain gears up and gets faster. It says, oh, it's really loud, right? It's really annoying. And so they realized that there was a faster rise time response to the way the brain synapses went if you were anticipating an impulsive sound. And so that led to the impulse time weighting, which had a fast rise time and a slightly slower than slow decay time so it's asymmetric compared to the fast and slow weightings. And so that led to that standard becoming important for a while. And it was actually dropped in the descriptions of what sound level meters should or need to do, with the exception of an addendum in the IEC 61672. In other words, they're allowed to be there. There still are some community noise standards that use the difference between the average of the impulse and the average LEQ, both A-weighted, of the signals, because of that asymmetry of the rise time and decay time of impulsive noise, if there's a large difference between the impulsive average and the regular LEQ average, then you can add a penalty for impulsive noise of a noise. And that's about the only place it exists in standards, and there aren't that many out that do use that impulse noise anymore.
I wanted to point out one more thing about that. We just have a little blurb in the paper on the practical tips that you have to use proper care when interpreting the results if you do use an impulsive setting. And that if you have short repetitive sounds that occur at intervals less than 1 second, that you need to really consider what it's doing because of that asymmetry, because the time after is 1.5 seconds, the time constant. And so that could potentially include the sounds then from the next event.
Yeah, it's important to understand how your instruments are working. That's always right. So, and it's been a while since I've come across a community noise standard using that impulse, but I'm sure they're out there.
All right, I'm reading through other questions, and some of them we've addressed and some not. Maybe you want to circle back to sound level meter apps a little bit. It's always a kind of people want an app that will do, I already paid, I paid $1,200 for my phone. So do I need to buy a meter? Can I just use an app? So Sunit was asking, essentially the NIOSH app doesn't do spectra. And is there anything that has had like a paper written on it that will do narrowband or 1/3 octave band spectra? I'm not aware of anything.
So I would recommend maybe we re-ask that in the next session.
Okay.
One of our presenters in the next section who can't talk right now is Owen King from University of Hartford. And Owen's done a lot of work with sound level. His students have done a lot of work with sound level meter apps. So he's pretty well versed in that market. And I think he can speak to that probably better than I can for sure. So if you're looking for literature on that, Owen's got some published papers out there on sound level meter apps. So look up his name and you might find some information on that.
Just a note on a lot of those apps, they have to be written right to be accurate with modern phones, because modern phones have noise canceling functionality in their microphones, and those things have to be software disabled. The microphones, of course, don't have a directional pattern that you could, meet any kind of standard with, but they're out there. So there's a great variety between these apps and how they work and how they don't work. And it changes by software version. And this is one of the reasons why Androids are so difficult, because they're not consistent across they don't always offer consistent operating systems in the way they handle the different hardware configurations of these advanced phones.
All right.
I mean, that's even true for iPhones, even though it's one product by one vendor, but Apple has a minimum of 2 suppliers for each of their components. And I know in past models, their microphone capsules could vary widely, even among the same phone, depending on which vendor you get.
Well, good discussion, everyone. We need to wrap this up.